Hello, this is Concrete Path and the lecture for your RCC that we call as flanged beams. We have to go for the flanged beams. Okay, let's take that flanged beams. Flanged beams. So we say that your beam is there and slab is also there. Beam is there and slab is also there. And we have n number of beams. They are casted together with the slab. They are casted together with the slab. They are casted together with the slab. Okay. So that we call as monolithic construction. That slabs and beams casted together, slab and beam casted together, that you call as monolithic construction. Monolithic construction. Monolithic construction. Monolithic construction. Okay. Then we can have a span also, effective span also there. Let's say this is our one of the beams. This is one of the beams here. Let's say this is the beam, and it's extending to the continue that because let's say there is some support here and one more support is somewhere here, so it becomes a L effective span of that beam is LE. Okay, LE is the effective span of the beam. Similarly, there can be many number of supports. There can be many number of supports. Let's say beam is continuous, and the entire slab is also continuous to the end. That's if there is one more support here, one more support is somewhere here, I would say we have different number of those panels, and I would say the slab is continuous. Yeah, I would say that what you call as, let us remove this part. I would say that your beam is continuous. If the beam is continuous, that means we have n number of supports for a single beam. For a single beam, we have n number of supports. Then for a particular beam, if you want to draw that BMD, let's say this is one of the beams. Let's say this is one of the beams we have, and we have a few number of supports because the system is continuous. And if I want to draw that because of the loads, if I want to draw that BMD, I would say your BMD would be some sort of diagram in this way. This is our BMD for this what you call as continuous beam. This would be some sagging positive bending moment near the mid span and hogging bending moment near the near the supports. So hogging bending moment near the supports, near the supports, near the supports, and some sagging bending moment near mid span. Now we are going to see what we are going to see first that the concept of as individual beam. Let's talk about this system, this monolithic construction. I would say if there is some, if this is the width of the web, we call this as web. This beam, the width of the beam, actual beam, we call it as width of the web. And I would say the center to center distance would be, let's say that this one is your L1. Let's say this one is your L1. Let's say this one is your L1, and this is your L2, and this is your L3. Okay, clear span. This is clear span between the beams, and there is some width of the beam. Let's say the width of the web is same BW, BW, BW. I'm going to say that the slab, the total load of the total loads on the slab would be distributed on these different beams. If we talk about a particular, beam, let's say this one, number one, I would say a part of the slab from the left side and part of the beam, a part of the slab from the right side of this particular beam one, that total load would be transferred to entire to this beam entirely, to this beam entirely. So I would say this contributing area, the total loads on this part of the beam, on total part of the slab, on this part of the slab, that total contributing area would be uh, set as a loading for this beam, beam one. So total load of this one. So I would say there's some sort of beam. We can say there is some sort of beam in this fashion, which is having some contributing area from this side. Let's say there is some effective length LE, and we have some width of B. Let's say this is some width of B, and we can say this width of B is equals to some width of BW plus some L1 by 2 plus some L2 by 2. So this is the what you call as that width of the flange. We call it as flange, top part. That's in the slab portion, So we say that there's some sort of a beam that's we call as flange beam developed. And similarly from the end side we have a kind of L-shaped beam formed. We have some sort of L-shaped beams formed. That's it's having some contributing area only from the right side, of that web. So this is some contributing area for this beam. So it's having some width of, it's having some dimensions in the fashion that if this is BW, so the top B equals to some L1 by 2 plus BW. L1 by 2 plus BW. L1 by 2 plus BW. Okay. So we said that similarly we have one more beam that we can say this part from the left side we have L2 by 2 up to this point, and from this side we have L3 by 2 for this beam, and width of that beam BW. So this beam becomes in this fashion. And the total loads are acting from the slab on this portion, contributing area. We call that as contributory area. Then we said that now if you want to design now these entire beams, either it can be L type or it can be T type. So we have two different types of flanged beams formed. One is your L type and next one is your T type beams. Flanged beams formed. But if you see that these flanged beams, they are continuous throughout the span. If they are continuous and somewhere we have, I would say at some point, let's say at near the support level, we have same sort of beam. If I extend this beam somewhere here, if I extend this beam somewhere here, I would say there is some beam in this fashion. There's some beam section. If I cut this section, I would say that there is some section of the beam that's T type. But it's near the support. Okay, and one more of this beam near the midspan. Let's say this is a midspan. I am cutting the section, and I am showing only this one of the particular beams, and I am showing only one of the particular beams. I would say there is one more beam near the midspan. It's near the midspan. I have to design these. What you call as these two kinds of beams. The design means you have to say how much steel we have to provide. AST, head of the steel for tension reinforcement. Now, if we talk about that hogging bending moment near the support is there. Near the supports where hogging bending moment developed. Let's say the hogging bending moment is developed near the support level. I cut the section near the support level. Hogging bending moment is there. Let's say this is some beam and hogging bending moment is there. That means there would be some neutral axis and there is some hogging bending moment in this fashion. Some hogging bending moment. So because of that, I would say the top fibers would be under tension. And bottom fibers under compression. And top fibers under tension for the hogging case. And if the top fibers are under tension, I would say the slab portion and some part of the beam, some part of the web, this part we call as web and this part we call as flange. That's also we can say this is slab. So slab portion would be, I would say the concrete. So that means the conclusion is that the concrete in the flange portion is ignored because that concrete is under tension. Concrete in the slab portion is ignored. Because we assume that our assumption in the limit state of flexure is that we ignore the tensile strength of concrete. Concrete in slab portion is ignored. And we design this part, we design the beam at the supports as a rectangular beam. So we design the beam as a rectangular beam. Rectangular beam in this fashion. We're going to design it in this way that we have width of B and dimensions of that effective depth T. So we design it as a rectangular beam near the near the supports. Yeah. If we talk about that near any midspan, we have a positive bending moment near the midspan. So at the midspan, we have a positive bending moment. That means positive bending moment is applied. M sagging bending moment, and because of that, we have top compression, bottom tensile, bottom tension, top compression. This is C, this is T. That means the top would not be ignored now. We can ignore now bottom area, but that's less. We have width of the web that is lesser as compared to the slab. So it is designed as a it is designed as a flanged beam near the midspan. Designed as a flange beam near the midspan. So that means we do not we are not ignoring. That means slab is not ignored. Slab concrete is not ignored. Is not ignored. Is not ignored. Okay. Now coming back to our main one. Coming back to our main one. So either we have to design the beams as a rectangular beam, or we have to design it as a flanged beam now. So let's go for that. Let's go for that. Okay. One more kind of beam is there. If there is what you call as inverted beam, because of some architectural constraints, we might be having some beam in this fashion also. In this fashion. Let's say we might be having some beam in this way. We can call it as inverted beam. Inverted beam, and we design it as a rectangular beam. If the moments are, let's say, sagging, and we are going to ignore the concrete in the slab concrete ignored. Slab is at the bottom, so we can ignore the slab concrete ignored for design, and design it as a rectangular beam. We are going to design these beams as rectangular beams. Because we are going to ignore the concrete in the tension zone, we are going to ignore this concrete, so we can design it as a rectangular beam. Rectangular beam for the inverted beams. Okay. Let's go to our that particular flange. So either we can have L-type beam or we can have T-type beam. That we have flanged beams. We call them as flanged beams. Now, based on that concept, we have one of the beams. Let's take one of the beam here. Let's take one of the T beam here, flanged beam. We say that the loads from the slab, are delivered. Loads from the slab are transferred, okay, to this beam. Or loads from the slab itself are transferred to the beam, and there's the shear flow. There's some shear flow. Let's say there's some shear flow. There's some shear flow. There's some shear flow. And we say that because of some shear lag effect, there's some shear lag effect. We say your entire, let's say the width of the flange is more. If the flange is more, width of the web is 300. Width of the flange is, let's say, some 3 meters. That means 3000 millimeters. From the top, flanges wide. Flanges are wide. Let's say if the flanges are wide, we call that flanges are wide. What's going to happen? We say that because of this bending, flexural bending in compression, flexural bending, because of this flexural bending, we have compression at the top. Okay, we have compression at the top for M sagging. Okay, compression at the top. But the thing is that there should be some resistance to that. There should be compressive stresses developed in the section. But we say that the compressive stresses developed in the section is not a constant. We say that compressive stresses are not constant or uniform, in the flange portion. Because of those bending stresses, we say your flange is not providing that what you call as uniform bending stresses. It's not developing uniform bending stresses. So that bending stresses variation is some sort of. Let's try to have that. Let's remove this one. So the variation here is some sort of curved nature, and the bending. This is the compressive stress variation because of the bending, compressive stress variation in the flange portion. And this is, let's say the peak here is, peak stress here is developed near the what you call as web. Let's say this is some alpha. So alpha is your maximum peak stress developed, peak compressive stress developed near the web portion, near the web portion. But it's effect that compressive stresses developed, they are very less near the end portion of that flange, near the end portion of that flange. We say that your end portions of that flange, because of the shear lag effect, because of some shear lag effect, we say your flange, end portions of the flange are not effective, end portions of the flange are not effective in taking those bending stresses, are not effective in taking those bending stresses. So that the more closer you are to the web, the more closer you are to the web, the more stresses you are having in the flange, and it decreases as we go outwards away from the web. So this is your shear lag effect for this flanged beam. You would be studying this shear lag effect also in the steel structures also. So near that, at that time we would be understanding what that shear lag effect is. So as of now, we would say that your end portions of the flange are not fully taking those bending stresses. So because of that, we have some variation of that compressive stress variation in some curved nature. Then we define a term. Then we define a term. If this was your B, total width of the flange, B was your width of the flange, actual flange width, B was your actual flange width. Then we define a term that we call as effective flange width. Effective flange width. Effective flange width, that we represent by BF. We represent that as BF. So there's some effective width such that let's say the total force developed because of these stresses. Let's say the area here. Let's say the area contributed here because of those stresses, and there would be some length also from the back side of that beam. So that let's say some length of 1 meter we can take. So I would say the compressive force developed per meter, or we can say per 1 meter run, per 1 meter of that beam, per 1 meter, that equals to some area of that alpha peak, and we have some area multiply of that actual width. So there is some variation. That it might be some area, but we are having some peak, and we are having some actual width of B. It's not a rectangular area. We're not saying that this is a rectangle. There is some variation, and I'm saying that area having the peak of alpha peak, and there's some width of B, capital B. And if I want that same force, to be developed in the effective flange width also. So once I define this effective flange width, I would say this would be some lesser width. So there is some effective flange width that is lesser. Let's say this is some effective flange width. This is lesser as compared to, I would say this is lesser as compared to B. Now I would say I want that stresses to be uniform. I want uniform stresses in that portion of the flange. Uniform stress variation in the flange. In the flange. Uniform stress variation in the flange for this width of BF, for this BF, and with the peak intensity, with the peak stress, peak equals to alpha. That was the peak. This was the peak for actual stress variation. So we would say that there's some effective flange width such that the stresses, compressive stresses, are uniform in that particular width of that what you call as flanged beam, and that peak, that uniform peak, is equals to actual peak of that actual compressive stress variation of that flanged beam having width of B. But we are reducing that B to some BF such that uniform stresses have been developed on that flange. And we say that the total force that was actually developed because of that area, curved area under that curve, some area of peak of alpha and some width of b, and that same force should be developed in that small bf also. That should be also equals to c force because of that area per meter, because of the area that we have a rectangular variation. Let's have that rectangular variation. There is some variation such that the peak stress is also equals to alpha for the entire width. So then now I define this one also. Now I'm going to define now this one. So such that your total force of alpha times bf is there, and this alpha times bf is equals to the area under the actual stress variation in of that total width of b. Do you got it? So the final definition of that effective flange width is that it is that particular width of the flange in which the compressive stress variation is constant or uniform throughout that particular width of BF, such that the total force developed is some C force, and that's also equals to the actual C force that was developed because of that non-uniform stress variation for the length of B, actual B. That's your effective flange width. Okay. So we say that this flange width it depends on some parameters, and based on that we have few equations, and we can say on what parameters it can depend. On what parameters it can depend your effective flange width. Let's take that. Let's have a construction that's monolithic construction, and this is continuous system also. Let's say there's some continuous system. Let's say that the system is continuous. So case one is that system is continuous or monolithic construction. Continuous or monolithic construction. Monolithic construction. Okay, I would say let's take that this is your length L1 and this is your length L2, and there's some width of BW, there's some width of BW, there's some width of BW. Now I'm going to take that effective part. We already have delivered that content. Let's take that effective part for the T beam, for the L beam, I would say up to the midspan of this L1. Let's say this is some total contributing area, and for this one, well, let's say this is our contributing area for the second beam, that's T beam. Let's say this one up to the L2 by 2, up to the L2 by 2. Okay, so after that, this was your actual B for the T beam. This was your actual B for the T beam. Okay, now I had to define the effective flange width for this system. So let's take that outside. This is some width of B, actual width of B, and there's some depth of the flange, or we can say thickness of slab. I would say this is some thickness of slab. Okay, this is slab, and we call it as flange. Depth of flange. This is depth of flange. Thickness of flange, or we can say depth of flange. Thickness of flange, we can say depth of flange, or you can write thickness of flange also, but we write it as a df. Okay, let's say this is some df, and we have some bw also, but the system is continuous. Okay, system is continuous. Then we have the equation that T beam equals to width of the flange, effective flange is equals to bw plus 6 times df plus L naught by 6. I would say from the back side it would be continuous system. It would be also continuous. There would be some slow what you call as supports also on which these beams are hanging, on which these beams are resting. I would say let's have that perspective also. The system would be in this fashion. Let's say the support here is one support here, one more support is there. I would say the length here is effective length of LE. This is some effective length of LE. And what is L naught here? What's L naught here? I would say, what is this L naught? L naught is the, if you take simply support beams, what is the L naught? L naught is the center to center, or we say distance between points of zero moments. zero moments, zero moment. The 2 points where the moment is zero, the distance between those 2 points, that we have what you call as what we have. So this is, we have zero moment here, we have zero moment here. That means your L naught is equals to L effective for simply support beam. And if you take a continuous system, I would say the BMD is in this fashion. Okay, so I would say the bending moment is zero somewhere in a particular span. Somewhere moment is zero here, somewhere moment is zero here for the continuous system. So the effective span, so the L naught is some sort of L naught equals to, and we take it as 0.7 L effective. You have studied that columns also. There we have that derivation also, that L by root 2, effective length of L by root 2, that's why 0.7. So we take the L naught equals to 0.7 L effective for the continuous system. And same we are going to take, same value we are going to take for the fixed beam. We have that variation for the UDL, we have this variation in this fashion. We were going to take that also here also 0.7 L. Okay. So that's your L naught. That is distance between points of zero moments. 2 points of zero moments. That's consecutive to zero moment points. Consecutive. Okay. So we got the width of the flange as BW plus 6 times DF plus L naught by 6. And if the beam was L type, that's at the end side. We are having some width of BW, and we were having some length of L1 by 2 from the end side. Let's say that we're having some L type beam. For L type beam, we have the equation that BF is equals to, let's say this is some actual B. And we want to get actual that for that effective width of flange BW, that is also equals to BW plus, but we write here 3 times DF only. And in the second one, we write L naught by 12. And one more criteria is that we have to ensure also that your B effective is not more than this actual B. So we have to ensure that one more limit we need to apply, that this overall value, the BF you got from this equation, and this should not be greater than BW plus L1 by 2 plus L2 by 2. It should not be greater than that. It should not be more than actual, because we know variation is in this way. You can't have a variation for a large length such that peak is also same. How can that's possible? So your BF should be lesser than B. I would say your that BF should be lesser than BW and L1 by 2, L2 by 2. It should be lesser than that, be effective width. And similarly for this L type, I would say this overall value should not be greater than BW plus L1 by 2. Okay. This is the first condition, that's first case, that's continuous or monolithic construction. Now coming to the second case, that's we call it as isolated construction, isolated beams. So we are designing a beam that's separately, there's no connection with any other part of the system, no slab, no monolithic construction. That means the construction is not construction is monolithic, but the system is not. Yeah, you don't have to write in the previous case we write that monolithic construction. Monolithic was in the sense that we're going for all those beams and slabs, we're going for entire, we're going to take that as a single unit. We are making the entire thing in a single instant of time. Okay, monolithic, that means monolithic. And in this case also we are saying this is monolithic, but monolithic in the sense that this beam width, that web and flange is designed, is casted together, that is monolithic, but it is a separate thing. Once this is a separate thing only, then we call it as isolated system. We are only designing this particular T-type beam only, so that we have isolated system. And in this case we are designing L-type also, T-type also, some intermediate T-types also. So this is what you call as continuous system. continuous system. So you have to erase that monolithic in the previous one, monolithic. So let's go for isolated system, isolated beams. Let's call it, let's say this is some width of BW, and there's some capital B, there's some actual capital B, there's some actual capital B, there's some actual DF. So we would say for the T beam, your width of the flange that is effective, it's equals to BW plus L naught divided by L naught by actual B plus some 4. Yeah, and this should not be greater than, this should not be greater than B. This should be less than B. This should be less than B. And similarly for the L type, there's some actual B, there's some actual B, and there's some width of BW for the web, and there's some DF also. So for this one, we write BF equals to BW plus L naught by B plus 4, and we have this factor of 0.5, 0.5, and this should not be less, this should be less than B. Okay. Okay. So this is the end of that, those equations. So that means your effect, if I talk about that effective width, effective flange width, it's a function of L naught is a function of BW, it's a function of what we can say DF also. So it's a function of these things. That means it increases, we can say it is a direct variation with that. So it increases, your width of the flange increases with increase in the web, increase in the dimensions of web, width of web. Okay, increase in the span, increase in the span, increase in the span length, increase in the thickness of flange, increase in the thickness of flange. So it can increases, we can have a direct relation here. So it increases with the increase of those particular values. Okay. We also say that BF also depends on loading, concentrated or distributed. Now let's take now what you call as problems. Now let's go for the analysis of that flanged beam. Let's go for the analysis of the flanged beams. Analysis for your flanged beams. Analysis for flanged beams. Let's try that. Analysis for flanged beams. Flanged beams. Now we say that there's some general T beam. There's some general T beam. Now we are taking that effective flange width directly. We are taking effective flange width now directly. Okay. So there's some effective flange width. There's some depth of the flange, thickness of the flange DF, and there's some width of the web BW, or we call it as also rib, or we can also call it as web. And we are placing some, and now we are solving for a general case, that is moment is sagging. Moment is sagging, that means the tension zone is in the bottom side, so we are placing steel reinforcements somewhere in the bottom side. Let's say there's some steel of AST, and the effective depth we can call effective depth of D here. Let's say there's some effective depth of D, small d. Then we have these 4 terms, and we are going to say, we are going to solve it in this way that that this equals to some beam of depth equals to D dash. Actually, we are saying in terms of effective depth, capital D would be there also. Let's say there's some capital D, and we are saying in terms of small d also. So there's some small d also, but we are treating it as a rectangular beam. This is a rectangular beam, and we are having some steel of AST1, and we say that there is one more beam that we call as imaginary beam. One more beam is there, similar to that of doubly reinforced beam. We are saying in the same fashion, but here the concrete is placed not at this part, but concrete is placed at the ends. Let's say there's some concrete here, and there's one more concrete part here also. So this is concrete. This is the concrete here, and this concrete is shown for this part. So this is concrete, and I would say this dimension here, this part of the concrete dimension would be total BF by 2 minus some width of the web by 2. So this is BF minus BW by 2. And we'd say there's some steel provided to you here at some location of such that the steel here is AST2. Steel here is AST2, and we have some concrete also at the top portion. So we are making that flanged beam in some sort of a rectangular beam and some sort of a that area above area in a particular concrete area of dimensions. I would say the dimensions for this concrete that's here, that's the dimensions here. I would say dimensions here is total width of B total of that's 2 times BF minus BW divided by 2. That is total width of BF minus BW. And we have depth of DF. So area of that concrete is BF minus BW into that what you call as DF. Now the thing is that we know that how to design a rectangular beam. We know that how to design rectangular beam, singly reinforced beam. That's easy. This part is easy. And for this part, there is a concern. For this part, there is a concern. So we have a tricky point here. So the concern here is the calculation of neutral axis. Calculation of neutral axis. So this is the main concern for this flanged beam. What should be the neutral axis location? What is the actual neutral axis location? For the first part, we can easily solve that where should be the neutral axis location, and for the second part, it's a mess, lot of work we have to do. So based on the location of neutral axis, we can have three different cases. Do you know that stress block for that singly reinforced beam? Do you know that what was the stress block? Stress block was in this fashion. Do you know that? The stress block. There was some T, and there was some neutral axis location XU. This was some neutral axis location XU from the top. Neutral axis location, and I said that this one is your 3/7 XU, and this one is your 4/7 of XU. So we have, based on this stress block, we had three different cases. For this what you call as flanged beam. For this flanged beam, let's take one by one. Let's study that the second part of the beam. Let's study the second part of the beam because this is the main concern for this flanged beam. Let's take that now. I would say, based on the calculations of XU, let's say the first case that neutral axis location is in flange portion. That means the neutral axis is somewhere in the flange portion. Neutral axis is somewhere here. So we got some neutral axis near the web portion. So the strain variation would be in this fashion if the neutral axis was in the what you call as in the web portion, in the flange portion. So first case is that neutral axis in the flange portion. Let's try to have that picture. I would say the strain variation would be, if this is DF, let's try to make it a bigger picture so you can have a better understanding. Okay. So first case is that I'm saying if the neutral axis location is in the what you call as, if the neutral axis location is in the flange portion, that's in the slab portion. Okay. So if the what you call as, if the neutral axis is in the flange portion, let's calculate only up to the level of that steel. Let's say steel is somewhere here. Let's remove this one and place that. The bars are placed here. Let's say this is the neutral axis that location for your what you call as steel. Okay. Let's go for the strain variation. For the first case, that's neutral axis is somewhere here in the flange portion. So it becomes a bigger strain variation. Let's forget that. I would say the strain variation is in this way, some sort of in this way. Let's say this is some strain variation. This is the strain variation we have. That is, we say xu is in flange portion, is in flange. So first case, and for that, can you draw the stress block? Can you draw the stress block? I would say there's some T force, there's some T force, there's some T force. We can know that 0.87 FIST, and there would be some stress block. But because the neutral axis is in those what we call as neutral axis is in the web portion, that means the entire stress block of that entire concrete stress block compression, that is all included here only. That means the stress block would be in this fashion. That means this is 3/7 XU and this is 4/7 XU. So that this is your XU, neutral axis location. And there is some C force somewhere here. That force we can calculate that. So this is our first case, that the XU is in the flange portion. Now second case is a possibility that if the neutral axis is not anywhere in the flange, that means neutral axis would be somewhere in the web portion. So second case is that neutral axis is in the web portion. Neutral axis is in the web portion. Let's have that second case, that neutral axis is in the web portion. Let's say somewhere here, neutral axis is somewhere here. Let's say the neutral axis is somewhere here. Neutral axis is in this portion. And can we draw the strain variation? I would say the strain variation would be in this way. Okay, this is the strain variation. Forget about the strain variation because main concern here is stress block. So I would say the stress block would be that up to this point, this is XU. Let's make by a straight line. I would say for the second case, that means if this is neutral axis up to this point, we can have a stress block. We can have the stress block, and initial portion is that it is a constant. It is a constant value. After that there is a parabolic variation. After that there is a parabolic variation. Do you know that? And let's remove this to get the confusion out of that. So I would say at a particular, if this is DF, let's say this is DF, total DF, that width of the thickness of the flange, this is DF. So at the level of DF, we would say, let's zoom it. I would say that this is the DF line. This is the DF line. That means this part is total DF, but the 3/7 XU, 3/7 XU. Let's say this is XU. This is XU for the second case, and 3/7 is up to the straight that constant stress value, 3/7 XU up to this value, and this part is your 4/7. This is your 4/7 XU. So that means what can you get from this equation, from this diagram? I would say in the flange, in some part of the flange, in some thickness of the flange, there is a parabolic part also. Can you see that there is a parabolic part for this part of the flange? For some part of the flange, there is a parabolic part, and after that, there is one what you call as, there is a, after going to DF, there is a little bit of parabolic part outside the flange. That is some part of the flange, some part of the parabolic part is in the web. So for this case, let's try that to get the picture. Let's write some part of parabolic part of the stress block, parabolic stress block is in the web, is in flange, and some part is in, and some part in the web, some part in web. Okay, this one, and after that we can have that T force also somewhere here. Let's say there's some T force also at the level of steel. There's some T force. And third case is that you can write that this is the second case. Let's try that. This is the second case, that XU is in web, that neutral axis is in the web, but that 3/7 of XU, is it lesser than DF or is it greater than DF? Based on this one, what can you tell? If the DF was, if this was DF up to this level, that 3/7 is lesser than DF. That means DF is more than 3/7. Can we say that? For the second case, DF is more than 3/7 of XU. This is second case. And third case is possibility is that we can have a, let's say neutral axis is somewhere. Let's say the neutral axis somewhere. Third case, let's take the neutral axis somewhere here. Let's say the neutral axis is somewhere here. Let's say the neutral axis is somewhere here. Neutral axis is here. Let's say this is neutral axis for the third case. That means neutral axis is in web, but the things, let's have that part. So that means the entire part, that is XU. So this is your XU. This is XU. Okay, let's remove this part. Let's remove this line. If this is XU, and we know that this part is DF, this part is DF, okay, this part is DF, and let's try to make the stress block. Let's have the stress block. Let's draw the stress block. I would say the stress block is some sort of in this fashion, some sort of straight, then after that parabolic, straight and parabolic, straight and parabolic, straight and parabolic. Let's say that this part is 3/7 of XU. Let's say this is 3/7 of XU, and this part is 4/7 of XU. And this is your neutral axis location. And what can you tell that based on this one? Can you tell me what is the stress variation in the entire flange width? In the entire flange thickness, can you tell me what is the stress variation? If the if the peak value here is, we know what's the peak stress here. What is the stress here? Is that 0.45 FCK? Is it 0.45 FCK? Is it 0.45 FCK? That means for the entire DF thickness of the flange, you have a constant that value of 0.45 FCK. Can you say that? So entire DF is having stress constant stress of DF that 0.45 FCK. Entire DF is having constant stress of 0.45 FCK. But in the previous case, I would say some part, only 3/7 of that XU is having constant stress. After that, some part of the DF is having non-uniform stress variation in the form of parabolic nature. Can we say that? Can we say that? I think so. So that means here we can have that 3/7 of XU is more as compared to DF. Can you say that your 3/7 of XU, because 3/7 of XU is below this DF line also. This is your DF line, below the DF line. See, if this is DF line, below this DF line even we can have a constant stress variation. So I would say 3/7 of XU is greater than DF. So 3/7 of XU is greater than DF. So we had three different cases, and based on these, we had three different analysis for that. So three different kinds of problems we can take. First one is that we said your neutral axis is in the web flange portion. That means entire stress block was in the flange portion itself. So there was no worries. For that area. For that second beam, we take imaginary beam, but the area was somewhere here. Some area was here also. And this is all this performance is only for calculation of that particular force of C. So write this point here. All this calculation and concept, all this concept is related to calculation of that force here, and here. Calculation of that force C2. That calculation of that C2 force, we are doing all this stuff. All this stuff is performed in order to get that value of that C force here in these two segments. Okay. Okay. Now I would say let's go one by one. Now. Let's go for the first case. Let's go for the first case now. I would say your neutral axis is in the flange portion. That means your XU is less than DF, or it can be also equals to DF. So that means if there was some flange, and neutral axis is somewhere here, that means this part is only having compressive, and bottom part of the concrete is getting ignored. This we can have ignored, negative. This is ignored, and we can have stress variation in this fashion. So I would say how do you solve for this problem? I would say there is some effective flange width of BF, and we have some dimensions of total DF. We have some total dimensions of DF, and we have some XU also. And do you know how you solve a beam? How you solve a singly reinforced beam of dimensions B and D, that small d, such that neutral axis is somewhere here at the location of XU. Total effective depth was small d. Effective depth was small d. Do you know how you solve that C force and T force? What was the C force equals to? 0.36 FCK B XU, and T force was 0.87 FY AST. And moment of resistance was equals to 0.36 FCK B times XU D minus 0.42 XU. And based on that, because we are saying that this C force is corresponding to a width of B, so this C force is corresponding to this value, this part of the because this part is having compressive force, so this part of the dimensions is taking that compressive stress, this part of the dimensions of the section, so this B. So similarly, if the positive compressive stress is in this part that's above the neutral axis, so if this is positive, so we are going to take this as a singly reinforced beam, or a rectangular beam of dimensions BF cross D is effective depth of. So if I make it as a that singly reinforced beam with the dimensions of BF and some effective depth of D, such that neutral axis is at XU less than DF, and I can have the variation in this fashion. This is XU, and there's some T force also, and there's some C force, and C force is equals to 0.36 FCK, and I would say BF. So there's a difference here. We are going for the actual BF. That's taking the compressive stresses, because your flange portion is taking the compressive stress. So we are keeping that entire BF here, 0.36 FCK BF, and we have actual XU. And similarly, T force would be equals to 0.87 Fy, and there's some steel AST here, And if I want to calculate that actual location of neutral axis, I can solve that. XU equals to 0.36, 0.87 Fy AST, and divided by 0.36 FCK times B times flange. BF we have to write here, BF. So once I got the XU, I can then find XU limiting equals to K times D. Then you compare them, and if you want to calculate moment of resistance, you can calculate moment of resistance also. Moment of resistance at the rate of XU actual, and that we have 0.36 FCK B F, and we have XU D minus 0.42 XU. So this is the calculations for the first case. That's easier case. So first case is easier case. Let's remove the first case now. Okay. Now second case is let's talk about the third case first. Let's say this is third case, case C. Let's talk about the case C, that XU is in the web portion. That means if the XU was in the web portion, XU is in the web portion, and 3/7 of XU was greater than DF. That means if this is DF, yeah, let's have the diagram. So neutral axis was somewhere here. Let's say the neutral axis was somewhere here. This is neutral axis, and the stress block would be in this fashion. Let's have the stress block. That means the entire DF. This is the entire DF. Entire DF is having stress of 0.45 FCK. Entire DF is having a stress of 0.45 FCK. So and this part we are doing for the calculation of that C2 force in the beam that's having those concrete that's above some in some imaginary beam. So this we are doing it for this concrete we are doing it for. And so this T beam can be solved in this fashion, that this T beam is equals to one of the beam as a beam, rectangular beam of dimensions BW and some effective depth of small d, and plus one more beam that is also imaginary beam, but we have some concrete here and we have one more concrete here, and the dimensions we can have BF minus BW here and divided by 2, and we can have entire, when you multiply it twice, so we can have a total concrete width of BF minus BW, and we have some thickness of DF. We have some actual thickness of DF. Up to this part, up to the DF part. Let's have it up to the DF part. Let's take it up to the DF part. If this is the level of DF, I would say we have concrete up to the level of DF. So this part is equals to BF minus BW divided by 2. And first case is that easy. I would say for the first case, as the neutral axis is here, I can easily solve that C force in the first case. I know that C force in the first case corresponding to, so if I make the stress block for the first case, there's some C1 force and there's some T1 force. C1 force is equals to 0.36 FCK, and some width is there and some XU is there, and similarly 0.87 Fy, some AST is there. Let's say there is some steel AST1, and in this case there is some steel AST2 in the second beam, and corresponding to the first beam I had the dimension of width. What is the dimension of width we have for this beam? That's a rectangular beam. I have to keep this as a BW. Here we have to keep as a BW. Okay, now based on this one, I can easily solve the moment of resistance for this part also. Moment of resistance 1 is equals to 0.36 FCK B W XU D minus 0.42 XU. That's easy. But for the second case, I would say the stresses are uniform. In this part. If I want to make the stress block, let's try to have the stress block. Stress block for the second case. This is very important. I would say there is some T2 force of 0.87 Fy AST2. There is some T force of 0.87 Fy AST2, and there should be some C force acting at the centroid of this area. Let's say the total area is, this is the total area of BF minus BW, and we have some depth of DF. So this is the entire area of that second beam, entire area of that concrete in the compression side, and neutral axis is somewhere here. So I would say the stress block would be in this fashion. That entire part is having stress constant stress of 0.45 FCK up to the entire DF portion, and after that we say that it should have been in this fashion. That neutral axis was somewhere here, but we are calculating only for this part. Actually that 3/7 of XU is up to this level, but our DF is lesser than 3/7 of XU, so we are going to take these calculations. We are going to take that C force corresponding to this part. So there is some C force, C2 force, that is equals to some stress, area of the stress block. This is the area of the stress block, and some dimensions of, what is the dimensions of that cross section? So dimensions of that cross section is equals to BF minus BW. So this is the C2 force we have. This is the C force we have. This is similar to that of a doubly reinforced beam. We were calculating that C2 force. In that case, the difference here between DRB and this one is we are not placing any steel in the compression side. ASC, we are not providing any ASC. This is the difference we have with respect to that DRB. Do you got this part? Because the stress is constant for this width of, for this flange depth DF, constant stress. So I would say this total force C2 is equals to area of the stress block area of the stress block, and some section width of PF minus PW. And similarly, T2 force is 0.87 Fy is T2. And if I say, if I want to get the actual neutral axis location, so the first step is, if I want to get the actual neutral axis location, so I would say equating C equals to T. So I would say C1 plus C2 equals to T1 plus T2. Similarly, we are doing it for DRB also. So let's go for the C1 plus C2. Let's write that C1 plus C2. So the equation becomes 0.36 FCK BW XU plus the C2 force we have 0.45 FCK DF BF minus BW, and that should be equals to total. Let's say the total steel is AST, and I would say 0.87 Fy AST, and equating it, and I can get the location of, so get the location of neutral axis. Once you got the location of XU, then you can have XU limiting also, and we should ensure that XU limiting should be lesser than, yeah, XU it should be more than XU actual. We have to ensure that this is that what you call as this limiting is greater than XU, and that means this section is under reinforced, and corresponding to that, I would say moment of resistance at the rate of XU equals to some C1 Z1 plus C2 Z2, and why your lever arm 1 corresponding to a rectangular beam, so lever arm 1 corresponding to the rectangular beam, so do you know that was D minus 0.42 XU. So that we write 0.36 FCK actual width of that beam BW, and XU, then we write D minus 0.42 XU, and plus second beam is that C2 force of 0.45 FCK, and actual width of that BF minus BW, and we have that we have that DF also. And can you tell me what is the lever arm for the second for this second moment that can be developed because of internal couple? I would say this force is acting at, what is this depth here? Can you tell me what is the what is the centroid location from the top? Is it df by 2? Is it df by 2? And if this is small d, if this is the small d at the level of steel, if this is small d, can you tell me what is the lever arm? What is the lever arm? Is that d minus df by 2? Is it d minus df by 2? So I can write this lever arm of d minus df by 2. So this is our second case of the problem, that this is our moment of resistance. Okay, let's go for the third case. Yeah, we forgot that. Yeah, that is in the design part. We are going for that also. Let's go for the third case now. In the second case, what we said, in the second case, that is the case C. We said that your neutral axis is such that your 3 by 7 of XU was somewhere here. So this was your 3 by 7 of XU. That was greater than DF. So this was DF, but 3 by 7 was XU was up to this part. That means constant stress variation was up to this part. After that, we have parabolic variation. That means the stresses in the flange was constant value of 0.45 FCK. Okay, now going to the third case. Let's go for the third case now. Let's take the third case. Let's add this. Okay. This is the level of DF. Okay, this is the level of DF, and from the top we have the level of top fiber, and there is some steel at the level of this what you call as DF. Let's say this is some steel here, AST, and we have this small effective depth of small d. We have some effective flange width of BF, and we have some effective width of that. We have some width of web also, BW, and there is some DF also, thickness of flange. So this is the actual case B. This is the case B, and in this case we say your neutral axis is in web, and your 3 by 7 of XU was actually lesser than DF. That means DF is more. DF is more. Yeah. If the DF is more, let's try to expand it a bit. Let's try to expand it a bit. Let's say DF is more. Okay, I'm gonna extend it. Okay, let's go with this. Let's go with this one. Let's go with this one. Let's say that DF is up to this point. Let's say this is the DF, and we can treat it as what you call as this can be equated to a singly reinforced beam of a rectangular cross section of dimensions BW and some effective depth of D, and we are having some steel of AST1, and there is some stress block. The stress block for the first case is that we have some T1 force and we have some C force. We said that neutral axis is somewhere in the web portion. Let's have the neutral axis first. Let's take the neutral axis. Let's have the neutral axis. Okay. Let's say the neutral axis is somewhere here. Let's go थोड़ा सा ऊपर चलते हैं. Let's say neutral axis is here. This is the neutral axis. This is the neutral axis. Okay. Now, if you want to make the stress block, I said that 3 by 7 of XU, 3 by 7 of XU is lesser than DF. If this is DF level, that means 3 by 7 is only up to somewhere here. So this is 3 by 7, and it becomes to 0 here after going to XU. So this is the variation. Up to this point, I would say this is constant. After that, there is parabolic variation. So this part we can say this is 3 by 7 XU, and this part we can say this is 4 by 7 XU. And for the first case, it is easy. It's easy. We don't care about where is the neutral axis. We don't care about that for the first case. This is the C1 force, and C1 force we already know that is easy to calculate, 0.36 FCK, and the actual width of that section, that is BW, rectangular beam BW, and we have that XU actual, and T1 force is already we know 0.87 FY AST1. Okay, that's easy, and we have that lever arm of D minus 0.42 XU. This is your lever arm Z1. That's easy. And for the second case, so I would say this total beam, T beam, can be equated in this fashion. One is your rectangular beam, and one is your imaginary beam. One is your imaginary beam, such that the concrete is only here. The concrete here is in here, up to this point, up to the level of DF. Up to the level of DF, we have the concrete. Up to the level of DF. So this is our concrete. Here we know this is BF minus BW divided by 2. Okay, and these dimensions we have DF. The dimension here is DF. And if I want to make the stress block for this, let's go for the stress block for this part. I would say the stress block is in this fashion, that it is parabolic up to some point, such that this is some 4 by 7 of XU. This is 4 by 7 of XU. And after that, there is 3 by 7 of XU. 3 by 7 of XU. And the intensity here is maximum stress value in the concrete side, that is 0.45 FCK. This is the maximum compressive stress we have, 0.45 FCK. And we have the level of DF. Where is the level of DF? I think this is the level of DF. This is the DF level. This is DF. This is the DF level. Can you see that? This is the DF level. That means, what can you get from this curve? What can you get from this curve? So our effective concrete is only for the, concrete is only for the depth of DF. Concrete for DF depth. So we need to calculate the stresses for the DF depth. So from that, we need to calculate the stresses for the stresses. Let's say this is some stress 2, because we are talking about beam 2. Stress 2, calculate. How do you calculate that? If the variation is somewhat in this fashion, if this is some depth of DF, and the variation is somewhat in this part some sort of in this way. That's stress. This is the stress variation we have. After that, in the web portion we have it becomes 0 in the web portion. This part is web. We don't care about the web. We are worried about the that DF part. We have this diagram. Can you get the area of this diagram? One is your rectangular part and one is your part of that parabolic. So how can you get that stress 2? That stress 2 is needed in order to get the actual C2 force. We need only this C2 force. How to get this C2 force? Because of this concrete of those dimensions of that total dimension of there is some DF and there is some actual width of BF minus BW. But your stresses are not constant. Stresses are not uniform as that of a previous case. In the previous case, stresses were constant for the entire DF. So we said that the C2 force is acting somewhere here at the centroid, and that was easy to calculate. But here we have a non-uniform stress variation in this case. I would say the top intensity here is 0.45 FCK, but it goes to some value here. I don't know this value. I don't know the value here. This part is 3/7 XU. So to account that effect, let's say this is DF. This is DF. To account this effect, so for this effect we have concept of effective depth of flange, effective flange depth. We call it as effective flange depth, effective flange thickness. That's right, effective flange thickness. That we represent as YF. And its equation is that this is equals to 0.65 DF plus 0.15 XU. We also write it as it is this way. I think we write it as in this way also. I think so. Yeah. 0.65 DF plus 0.15 XU. So let's have that under the stress block. This is our equation, important equation for this case. Okay. So the definition is that, okay. Now I would say, let's say that the total C force, total C force contributed by this one is some C2 force, and I want same amount of C2 force to be developed in that effective flange width such that the stresses are constant. Let's have that. So this is some thickness of the flange such that your stresses are constant, and that also having peak value equals to 0.45 FCK. This is that depth of that thickness of the flange. If the total thickness of the flange was DF and the variation of stress was in this fashion, let's have that. I would say variation of the stress was in this fashion. Now I want a particular value of DF, particular value of depth of flange such that stresses are constant. Let's say this is some value. Let's say this is some level somewhere here. I would say this is a value of YF. This is the value of YF, and that equals to 0.65 DF plus 0.15 XU, and such that the stresses here was actually 0.45 FCK, and here the stresses are also 0.45 FCK, and the stresses are constant for the entire thickness of the flange, for the flange thickness of YF. Similar to the previous case of that effective flange width, similarly we have effective flange depth thickness. So here we have some stress that is lesser than, let's say there is some stress. This stress is less than 0.45 FCK for the actual DF. Here we have one more stress that is also lesser than this part. So to convert it, so we are converting that actual DF with having non-uniform stress variation into some YF such that the stress variation is constant, and it also yields the same amount of force that was C2 force, and this yields some C2 force. Let's have the direction also. So that we can finally calculate that. Let's say that the C2 force is acting in this fashion, and that value of C2 is also same as that of a previous case, that the C2 developed because of this curve. C2 developed because of this curve, that is also equals to the C2 force developed because of this effective flange width into that air of the stress block into that actual width of the section. And I would say that stress block would be now in this fashion. There is some T2, 0.87 Fy AST2, and there is some C2 force having intensity of 0.45 FCK. This is the area of the stress block into some depth of the flange or thickness of the flange, that is YF, and the actual thickness of the section was this part. This was your actual thickness of the section. That was BF minus BW. That width of the that section, BF minus BW. So I got the C2 force also. If I compare it with the previous case, if I compare this one with the previous case was saying my C2 force was actually equals to this one. Can you see that? Can you observe that? In the previous case, we were talking about that for the entire DF we have stress constant 0.45 FCK. But in this case, we have stress constant only after the depth of thickness of YF. So where your YF, we have to substitute that value as 0.65 DF plus 0.15 XU. Now, once we got these, we can write that C1 plus C2 equals to T1 plus T2 in order to get the actual location of neutral axis. So let's try that. To get the location of neutral axis, let's have that total C1 plus C2. C1 force we already know, actual VW, XU, and plus 0.45 FCK for the width of BF minus BW, and we have this YF, and we have to convert that YF as a function of XU because we need XU. So we need to convert that as a function of XU. So let's write that 0.65 DF plus 0.15 XU, and that equals to 0.87 Fy total area of the steel AST. So why your this part is equals to YF, and from this one get the location of neutral axis, then compare with the limiting, ensure that section is under reinforced section. After that, calculate the moment of resistance. We can solve that is C1 Z1 plus C2 Z2, and that is equals to 0.36 FCK. The width of that rectangular beam of dimensions BW and effective width of D. So 0.36 FCK BW XU, and that lever arm of D minus 0.42 XU, and the C2 Z2 force C2 was 0.45 FCK, and for the what you call as for the width of BF minus BW, and we have that effective flange width of YF, effective flange depth YF, and we have that we need to get the lever arm for the second force. Can you calculate that lever arm for the second force? The centroid of the C2 force is here. It's at a depth of YF by 2 from the top, such that your lever arm equals to D minus YF by 2. D minus YF by 2. So in the previous problem, in the case C, that was your second case. In the case C, that was your second case. Our equation was also in this fashion. Except that your YF was replaced by DF, and your small YF by 2 was replaced by DF by 2. In that case, there the stress was constant for the entire DF, and centroid was here DF by 2. And in this case, that is case B, in this case we have stress variation was in this way after the DF. This was DF, but then I fixed that stress constant as a constant function after the value of YF, and centroid was here at YF by 2. Okay, this is the end of that analysis for your I think this is the end of the analysis for your what you call as flanged beam. And one more final touch is that the calculation of limiting moment of resistance, mu limiting. Let's say that XU limiting equals to do you know that what is the value of XU limiting? That's K times D. And let's say that we are talking about that neutral axis is in web portion, and we are going to take that 3/7 of XU as a critical point. 3 by 7 of XU. And if I take 3 by 7 of XU limiting for different grades of steel, let's take that case, that 3 by 7 of XU for different grades of steel. For different grades of steel, let's talk about first one, that is Fe250. 3 by 7 of XU limiting, that is K times D. K times D. And second one is that Fe415, that is 3 by 7 of 0.48 times D. Third case is that Fe500, that is 3 by 7 of 0.46 times D. Okay. Okay. I'm going to say that now I have to compare that 3 by 7 versus 3 by 7 XU limiting versus DF because the concern here was whether the entire DF is having constant stress or it's having some non-uniform stress variation also. So we are going to have a relation here, 3 by 7 of XU limiting versus DF to calculate the limiting moment of resistance. Now we got this value. Can you say what is this total value? This total value is equals to 0.227 D, and this value equals to 0.2057 D, and this value equals to 0.197 D. So this is almost equals to, I would say, almost greater than 0.2. Can I say this is almost equals to greater than 0.D because we are going for the critical value. So this is almost greater than 0.D. So this is almost equals greater than 0.D. So I would say for all values of 0. So for all values, for all grades of steel, that this was your XU limiting. This was your 3 by 7 of XU limiting. This was your 3 by 7 of XU limiting. That 3 by 7 of XU limiting comes to be equals to almost equals to 0.2 D. And if I say what is the ratio of dF by D, what is the ratio of dF by D from this one, dF by D, and I have to substitute the value of dF as 3 by 7 of XU limiting, 3 by 7 of XU limiting, 3 by 7 of XU limiting. If I substitute the value of dF as equals to 3 by 7 of XU limiting, 3 by 7 of XU limiting, that means this part is actually equals to dF, and that is almost equals to 0.2, or we can say that is greater than D, that we have 0.2. So finally is that so for dF by D greater than 0.2 for all grades of steel, we say that parabolic part is in dF. So parabolic part is in dF, because we are saying that if I have this value, if I have this value, what we get here? We get a value that this 3 by 7 of XU limiting is almost greater than 0.2 D for all values of all grades of steel you can have. That's almost greater than 0.2 D for all values of that 3 by 7 of XU limiting greater than 0.02 D. Now if I say that what is this value actually, if I calculate it at the limiting condition, that if I take this value as dF, that means dF should be greater than 0.2 D for all grades of steel. So I would say for dF by D greater than 0.2, that means this was derived for all grades of steel at the condition that that this was your 3 by 7 of XU limiting. That 3 by 7 of XU limiting is finally that 3 by 7 of XU limiting finally divided by D, that is greater than 0.2. That is greater than 0.2. So that means your parabolic part was in DF. So if your parabolic part, some part of the parabola is in flange, that means some part of the parabolic part is in the flange. So that means some part of the parabolic part is in the flange, this part. So for that calculations, if you directly say what is the dF by D ratio, if that is 0.2 greater than 0.2, then you can say that that we can have the equation of YF directly for the calculation of moment of resistance, limiting moment of resistance. So that value is equals to 0.36 FCK BW XU limiting, and that lever arm of D minus 0.42 XU limiting then plus 0.45 FCK BF minus BW, that actual that value of YF and value of YF and that lower arm of D minus YF by 2. So that is the direct calculations for the limiting moment of resistance for that particular kind of problem. If the dF by D is greater than 0.2, so you have this equation. So you have this equation. Final conclusion is that if your ratio dF by D is greater than 0.2 and if you want to calculate directly that limiting moment of resistance, you can directly solve by this equation, while your axial limiting equals to K times D. And corresponding to this YF, you have to substitute your 0.65 DF and plus 0.15 axial limiting. So that's also, we can have all the data we can have. So finally, we can say your moment of limiting moment of resistance can be calculated. So once I got the condition dF by D greater than 0.2, let's take the second case that dF by D less than 0.2. So second case is that if dF by D is less than 0.2, I would say you can directly calculate limiting moment of resistance equals to 0.36 FCKB XU D minus 0.42 XU limiting. We have to substitute here limiting, and 0.45 FCK BF minus BW, and then that depth of DF, then we have that lower arm of D minus DF by 2. So this is the equation, direct equation. If you want to directly calculate limiting moment of resistance, you don't have to get the actual location of XU and all that stuff. You directly use this equation. First you need to solve for the ratio of that dF by D. You would be knowing that dF by D ratio, it's easy. Let's say dF was some 100 millimeters and D was some 800 millimeters. So you would get the ratio either greater than 0.2 or less than 0.2. Accordingly, you have two equations for that. Okay. I think this is the end of the analysis. Now we have one page left. That is the design part. That is the design part of the flange beams. Let's go for the final part. That is design part of the flange beams. So once the section is fixed, that means BF is fixed, DF is fixed, VW is fixed, some effective depth is also fixed. So we only need to calculate that AST. We only need to calculate AST. That is the design of flanged beams. So design of flanged beam is only about calculation of AST. Flanged beam sections. So that's only about calculation of AST. So first case was if the, so now the problem is designed in this fashion. Let's see the problem design, how the problem is designed. We are saying that some moment is applied, some external factored moment is applied, this is applied moment, okay, because of some dead loads, live loads. We are having some bending moment, external bending moment, okay. And we say that we need to calculate what should be the AST required, what should be the AST that should be provided for this particular moment applied. So we say that calculate that MUE. Once you calculated that MUE, first case is that if I assume that, let's assume that neutral axis was in the flange. That means XU was either less than or equals to DF. So this is the first case, and I know that for the first case, what is the equation for the moment of resistance? Do you know that? That was 0.36 FCK capital BF, total flange width, and this one is your XU, and total was DF. So that we have equation 0.36 FCK BF, then we have XU, then we have D minus 0.42 XU. This is the easier equation we have from this part. So you have to substitute the value of MUE here. Once you substitute the MUE here because of the external loads, moment developed. So you are going to solve now equation in terms of XU, a quadratic equation, using scientific calculators. You substitute the equation here in the calculators, and you can get the location of neutral axis. Then you compare that with the limiting condition, and you have to ensure that your section is under reinforced section, And finally, once you got the limiting condition, once you got the XU, then we can say C equals to T, and you would say 0.36 FCK BF XU actual, and that's equals to 0.87 FY AST, and you can get the value of AST from that. After that, you can have some number of bars of some diameter, and that's your design of the section. Let's take the second case. If the thing is that if the value of XU was greater than XU limiting, if the case is that if the condition was that you assumed that your start was that you assumed XU is in flange. Once you check it that your value of XU, let's say that XU you got as 50 millimeters, and total flange width was 100 millimeters. Let's say DF was 100, and initially you assumed that XU was less than DF, and from the calculation you got XU equals to 50. That means the assumed thing that is correct. So this design is correct based on this assumption. That means you assumed correct, and calculations can be proceeded further. But if the thing is that you got some value of XU such that it was 105 millimeters, that was greater than DF, so that means the assumption you have, that is false assumption. So we need to get, once it is false assumption, once let's write that once you assumed, once the assumed thing is false, you have to go for the second case. You have to take the second rail that neutral axis is in web portion. Some web portion is there. So once you selected the neutral axis is now in the web portion, so finally that's your second part. So that's your final second part. Let's say that the neutral axis is in web portion. If I assume that neutral axis is in web portion and 3/7 of XU is greater than DF, that means the entire DF is having stresses of uniform 0.45 FCK. Can you say that entire that DF is having uniform stress of 0.45 FCK, and after that we can have this variation in the web. We can have this variation in the web. Okay, that means once you assume that your 3/7 of XU is greater than DF. So what is the equation we have for the moment of resistance? So I would say your external moments should be balanced by the equation of 0.36 FCK BW. Then we have that XU. Then we have D minus 0.42 XU. Then we have the second force of C2 and lever arm Z2. C2 into Z2. C2 was 0.45 FCK for the flange thickness of flange width of BF minus BW. And we have this depth of DF, and we have this that lever arm of D minus DF by 2. D minus DF by 2. Do you got that? And from this equation, you can have a quadratic equation again. Some function of x, some function of x square, and some constant of c. Let's say there is some equation ax plus bx plus ax square plus bx plus c, that we have to equate with 0. So finally, I'm getting the value of XU neutral axis, location of neutral axis from this equation. So that's all calculation we have to take. We have to solve it in the calculator. Get the location of XU. Now compare that. Now check that again. Now we need to first we need to check it whether our assumption is true. So once you got the XU location, let's say XU location was 109 millimeters. Once you got the 109 millimeters, and I assume that neutral axis was in the flange in the web portion, and if the DF was 100, okay, no problem. That means the assumption is true. That is the assumption is true. Okay, but we need to check also one more assumption was there, that I said your 3/7 of XU is greater than DF. I need to check that also. If this is true, if this is true, that means you can further proceed. If you further proceed, let's proceed further. That means we can now get the steel total area of the steel. So that means once you proceed further, let's proceed further here. So once you got the location of XU, then we can further proceed that C equals to T to get the to get the area of the steel, because we are designing the section, so we have to get the steel area of the steel. So I would say total force of C, that was C1 plus C2, 0.36 FCK BW, XU actual plus 0.45 FCK, and that BF minus BW, and we have one more part, that was, yeah, that depth of DF, and that should be equated to 0.87 Fy total steel of AST, T1 plus T2, that AST1 plus AST2, finally AST. So this we have to get AST, so get the AST, then after that get the number of bars accordingly. So this was the case when the assumption was true. Now second case is that if you assume that this was this one, and after the calculation of XU, you got some value of XU, okay, you got some value of XU. If this was not true now, if this was not true, that if this was not true, if this was not true, then we need to go further. We need to assume another part. We need to assume another part. That means we have to assume now that actual 3/7 of XU is lesser than DF. The final case is that we are going to assume 3/7 of XU is lesser than DF. Third case. So third case would be, if I assume, you can assume at any point. You can assume from this, even from the third step also. You can assume from the third step also. If I assume that 3/7 of XU is lesser than DF, that means if this is DF, 3/7 of XU is somewhere here. That means this part is having uniform stress. After that, we have variation of that stress after this DF level, and it becomes 0 at this point. So this is our variation. Actual DF is only up to this point. So we have to get the equation of YF. So that means we need to get the actual that effective thickness of flange, YF. So we need to use the equation of YF. So I would say that external moments can be balanced by external bending moments can be balanced by the equation of 0.36 FCK BW rectangular beam into XU and that lever arm D minus 0.42 XU plus 0.45 FCK BF minus BW, and we have this function of YF. We need to substitute that value of YF, that was 0.65 DF and plus 0.15 XU, and we have one more part, that is lever arm. That lever arm was D minus YF by 2, D minus YF by 2. D minus YF by 2. So so this calculation is very lengthy. This part of the calculation is very lengthy. So I would write this calculation is very lengthy. So this calculation is lengthy. So we need to solve the calculation. We need to solve for those to get the value of XU from the quadratic equation. So if I see that we have the value of the equation of quadratic, that is ax squared plus bx plus c equals to 0. We have to substitute here in the calculator, and for the value of c, we would say this is contributing to c. Let's have a color. This is contributing to c, and let's have the color so that we can get a better understanding. So let's go for the C. That's in the white. Let's write the equation in terms of some colors so you can have that also. I would say the equation can be written in the fashion that this is your ax square. After that we have that in the green part plus bx, then we have plus c. Let's say which part contributes to C. Let's say which part contributes to C. That is a constant value. MUE is a constant value. Okay, MUE is a constant value. And from this one, which of these is a constant value? I would say which one is a constant value? Yeah, this is here. We have to ignore here because the equation is bigger one. Equation is a bigger one. What is the equation we have? This one is the equation. Entire thing is the equation. This is the entire thing. That is the equation. So that let's say that this is constant C1. There's one more constant here somewhere. See, the value of DF is known to us. value of df is known to us. So there is some value here, there is some value we can have from this part, and we have to divide by 2, that we already know. And from this part also we have some constant. Let's try to make it in terms of that. Let's try to simplify it again, so that you can have finally that problem. 0.36 fck bw xu, and that d minus, yeah, let's say that in terms of only only this parameter. Now this is your d, then after that we have some xu. After that, we have one more part, that is 0.36 fck bw, and then we have this factor of 0.42, then we have this quadratic xu square, parabolic part xu square, and this part is negative. This part is negative. Can you see that? Because of this minus 0.42, this becomes negative. After that, we have 0.45 fck, 0.45 fck, and we have this bf minus bw, and that is a constant value, bf minus bw. And after that, we have this factor of 0.65 df, that's also a constant value. But we have to simplify this part. We have to simplify this part. One is your 0.65 df, and we have this multiply of d also. And one more thing is that we have this 0.65 df, we have to multiply it with 0.65 df divided by 2. And one more part is there, 0.65 df, we have to multiply it with that 0.15 xu by 2. So we got 3 parts from this one. And similarly, we got 3 more parts from the other part of the equation, that is 0.15 xu into d, then we have negative 0.15 xu into 0.65 df by 2. After that, we have one more part, that is negative 0.15 xu square, this also square divided by 2. So we got the 6 parts from this equation. We got the 6 parts in this equation. So it becomes a calculation problem. So let's forget that. Let's forget this part. We are going to see it in the problem itself. So we have to calculate. Finally, this part is lengthy. We have to finally say that this part is lengthy. Thank you for watching your analysis and design of your flanged beams. So next lecture will be designing for going for the problems of your flanged beams. Okay, thank you.